Well, hello everyone. Today we are going to be starting a brand new unit on chemical bonding. So if you'll get out your study guides and open up to lesson 1, we'll go ahead and get started. All right, now I know that you have some ideas of what chemical bonding is going to be all about from other previous science classes. But in this class, we're going to get into some pretty in-depth ideas about chemical bonding. And we're going to first begin to focus on why do chemical bonds form in the first place? And that's going to be our big question for today. And hopefully, by the time you're done with this video, you'll walk away with a very good understanding of why atoms come together to form these chemical bonds. Why is it so important? So let's start off with a definition of what a chemical bond is in the first place. So you can think of a bond as an electrostatic attraction. Remember, that's a force, an electrostatic force, that holds two atoms together to begin to make a compound. So I'm going to use a couple of tennis balls as an example or analogy, okay? Now, let's say that both these tennis balls are atoms. And as single atoms, they exist in nature, but they're not exactly happy existing in nature by themselves, which we're going to talk a little bit more in just a moment. So these atoms are going to tend to want to come together, and through an electrostatic force of attraction, they're going to start forming a bond between each other. And so instead of being two separate atoms, they're in a nice bonded structure that begins to form a compound. All right. Now, when we form compounds through these electrostatic forces of attraction, these chemical bonds, the new elemental or the new chemical properties of that compound are going to be quite different from the individual properties of each of these atoms. For instance, a good example would be like if we were going to form table salt, sodium chloride. So sodium, let's say this is sodium, an atom. Sodium atoms, they're metals, and they're very highly reactive metals, and especially with water. In fact, they're explosively reactive with water at times. And let's say this is chlorine, and chlorine is essentially a extremely toxic element. It's used as a disinfectant because of that. It's something that you definitely would not want to consume on its own. But the interesting thing is that when these two elements, sodium and chlorine, come together to form an electrostatic attraction, or in other words, a chemical bond, they form a compound of sodium chloride or table salt. And with that resulting bond or compound, we form very different properties. Table salt you can consume, you can eat safely in a certain moderation, of course, and not worry about it being overly toxic or extremely reactive with water. All right. So what I'm saying is that these new bonds that are formed to create these compounds, we create vastly different properties or new properties than what the individual properties of the elements that make up that bond or compound. Okay, so hopefully that makes sense. That's really important to understand, right? So again, though, we haven't answered our question. We've defined what a chemical bond is, but why do these elements come together, or these atoms come together and chemically bond together to form these compounds? Why do they just not stay apart? Well, the answer comes with an understanding of energy and understanding of the valence electron shell, okay? In short, bonds are formed during chemical reactions to help atoms fill their valence electron shells. So atoms that have unfilled valence electron shells are going to have an unfavorable amount of potential energy. So in other words, what we're saying is going back to our tennis balls, as these are single atoms that do not have full valence shells, right? They end up having a high potential energy state by themselves. So remember, the reason why electrons arrange themselves in the atoms in the first place is to try to minimize the potential energy, to try to lower that potential energy. But still, with unfilled valence shells, the potential energy is still quite high. So atoms have found a way to lower that potential energy state by filling their valence electron shells by creating chemical bonds between different atoms. When we essentially create that chemical bond, not only do we fill those valence shells, but we lower the potential energy state of those individual atoms now, okay? The only trade-off is that instead of being able to exist by themselves now, they must exist together in order to create that low potential energy state and have those full valence shells, okay? So the key is, the reason really why bonding occurs is to lower the potential energy state by filling the valence electrons shells, okay? And as soon as those shells are filled and that bond is created, then the state of energy goes down quite dramatically, actually. And those atoms are quite content now being bonded together and existing together in order to have that low potential energy state, right? So there we go. That's why chemical bonds form in the first place. Now, noble gases. Noble gases are the only elements on the periodic table that already have full valence electron shells. So they don't really have to go through chemical bonds or make chemical bonds because they're already got these full shells. So they can exist in nature by themselves and not bonded to any other element. However, all the other elements on the periodic table do not have full valence shells and therefore will be required at some point to chemically bond with other elements in order to have those full valence shells, all right? So what we're saying then is noble gases simply do not react. They're inert, all right? They exist as those single atoms. They do not therefore go through chemical reactions. All the other elements must react with one another. And a reaction is really the process of creating full valence electron shells and lowering the potential energy state of atoms, right? If a process does not lower the potential energy, then no reaction is going to actually occur. So again, the only reason why atoms interact and react with one another is to create a more stable or a lower potential energy state. One is by filling their valence electron shells, and then two is just creating that low state of energy that they can exist in and be happy in, okay? So if you look at the Bohr models or the shell models of these noble gases, you can kind of see a pattern here. All of the noble gases, with the exception of helium, have 8 valence electrons in their outer shells. And so really the magical number here is 8. In some cases it's 2, like helium, it can fill its valence shell with only 2 electrons. So what we have is known as essentially called the octet rule, okay? And in the octet rule, it basically states in order for atoms to have full valence shells, they must have 8 electrons in that shell. So again, the magical number is 8. However, a few elements such as hydrogen or helium, lithium, or beryllium, they're okay with having 2 electrons in their valence shell and having that as their full valence shell. Okay, and in this case, instead of calling it an octet, we usually call it a duplet. Okay, so it's really important to understand the octet rule. Again, the magical number for most atoms is 8 valence electrons in the outer shell, the valence shell, in order to have a full valence shell and therefore a happy low state of potential energy. Okay, so there you have it in a nutshell, why chemical bonds form. And that pretty much wraps up not only that question and answers that question, but finishes up this lesson. All right. So go back, study your notes, make sure you understand why chemical bonds form, understand the octet rule, the duplet rule, and understand that noble gases have already full valence electron shells, so they do not react like the other elements do. All right, so that's it for now. We'll see you until next time.